recent approach that that was developed. So here again, that what we are trying to do is that every time we are trying to train a detector, we have to have these labels, right? What happens if we don't have the labels? How can we detect a deep fake or synthetic content without using the labels? Just by simply dumping the images and then trying to find what is real, what is fake. So in this case, most of you who have taken mathematics as in the engineering or in your undergrad studies, you know about this SVD decomposition, singular vector decomposition. So if I take an image and then I can decompose it into multiple components, singular vector components, then I can start seeing that the real images and the fake images, they are slightly different. And the difference is very, very subtle, right? You can't really make it out. You see that the difference between the absolute difference between the real image and the synthetic image is so low, and at some point of time it starts shooting up. The performance, the percentage becomes more and more. So which tells that the singular value indices which are above 150 can be helpful in detecting the synthetic content. Now, if you use that idea, so these are the this is how the results look like. In the left side, you see they can be clearly distinguished, which are all synthetic, which are all real, and this pattern remains very consistent across different approaches. So there is, if I'm going to put a simple threshold, let's say the threshold here is around 0.75 or 78, then the amount of misclassification is still very, very low. Right now, if I know that I am fine tuning on this one, I can adapt the threshold based on this, but then it will start failing on this one, right? So the idea here is that by simply looking at something very, very simple, then I can recreate the I can detect the synthetic content. Okay, just to connect everything that we have been looking at so far, we spoke about this low rank SVD now. I said like any image is nothing but a matrix. From the matrix, you can decompose multiple components. And from these multiple components, you can try to reconstruct the images, which is again the idea that we discussed in another paper, right? So I have this original image, and then there is a unit. Unit is nothing but a unified U-like network, which is going from high level of convolutions to low level of convolutions until you reach a latent vector, and then you reconstruct it back again slowly in a pyramid manner. Right? So just if you are not familiar with unit, it's nothing but it's an architecture which goes like this, like this, like this, and then you have a latent vector, and then you invert it. Right? The information flows from this side. So this is the input image X, and then this is the output image X. Okay? It also works like that. I can have many encoders. Yes, certainly you can have. You can plug and play any of those networks there. So, but in that work, the idea was more to look at what can we generalize. So, by looking at the SVD components of each real image and the fake images, we could determine the single value decomposition, right? So, and the approach here is also training free. So we only train this approach, this particular network, and then we get the total loss. And then once I have the total loss, I just use the loss to say whether it's greater than threshold or less than threshold. So in this case, I'm not doing all the things that I'm doing. So I'm simply extracting the SVD, trying to reconstruct it, and then try to see the loss. And then based on the loss, I'm saying whether it's yes or no. So there is no classifier involved in this approach, right? So by doing such a simple mathematical, let's say mathematical analysis of the content, I can always say that whether the content is deep fake or in the sense synthetic or not synthetic. Okay, I'll not show the results here. Any paper that you see that you will have bunch of results. So the other aspect that I did not talk about today is how much robust are these methods. So very often we have this on the YouTube. You have this different resolution quality, right? You have 1080p, you have 460p, sorry 480p, and then you have different settings, 720p, and so on. So if I'm going to create a method which is purely based on 1080p, and then the deepfake comes in or the synthetic data that comes in is low resolution, let's say 480p, how much am I able to detect them. So if you look at such kind of compression, it could now come down to JPEG compression, it could come down to other kind of compression. In all these kind of compressions, you start seeing that the approaches start failing. So what you want is that if you want to have a generalizable system, it should also be robust against the compression, and it should also be robust against the common noise patterns such as Gaussian noise or a blur, or let's say the bad lighting condition and so on. The idea here is to show that there is still a lot of scope to improve for those of you who are trying to work on deepfake detection or synthetic content detection. There is this performance gap in this case, right? So we kind of bumped the numbers slightly up, but the gap is still here. So around 25% to 30% of accuracy improvement is needed. Okay, so I think I'll take this compression detection later. I know that you also need to go for a lab. So what I'll do is I'll go to the next part. Okay, so the block that we're going to talk now is about the different approaches that we have been talking about so far. All these GAN models, diffusion models, and then VAE models, and so on. How they can be applied for face recognition, specifically focusing on the applications around face recognition, such as attack detection, um, morphing attack detection, presentation attack detection, and so on. So before that, I wanted to show you some avenues where how they can be used, how synthetic data can actually be used, and then what are the upcoming avenues for research. Now let's just do a quick recap of everything that we have been talking about. We have this kind of networks that are typically RNN, which is used heavily in creating the deepfakes. And then you have the encoder decoder networks, which can be your variational autoencoder. It could be simple autoencoders, and then you have this other kind of VQ autoencoders, VQ variation autoencoders, and so on. And then there is also in the similar direction, we also have this GAN approaches, right? So there we have only depicted the vanilla GAN, but then you could also have a sophisticated architecture such as cycle GAN, and then you could also have a bit more sophisticated architecture such as conditional GAN, Pro GAN, PC GAN, and so on. This is to just recap everything that can be used. Now you see that there is a particular architecture, everything deals with input and then it's an output. So in between comes the latent vector, which we have been talking about for the last 3 days. Okay, so why do we need synthetic data for face recognition? What are the uses? So there are 4 uses that we can think about, right? So this is again a slide that I took from one of the recent survey, which was published about a year ago. And in this survey, they talk about what all opportunities are found for synthetic data. So now if you start from the left corner here, you see that the data can be used for training. Why do we say that we can use it for training? Because we can't collect millions of data, and even if we collect, we'll be able to collect only limited samples, right? So I can ask one of the participants here to give me the data for 1 day, and then if I ask him for second day, maybe yes. If I ask him for the third day, he probably will not be able to do that, right? Because there are so many other things you would have to take care of, not only organizing the data collection. So which means if I have to create multiple images of a particular person, then I could use these synthetic data generation approaches that we have been talking about. How they are all done, what are all the changes, we will see in a couple of slides. And then you have the second aspect. If you want to have different appearance of the same person, so how does Naveen look in on Monday morning, and how does he look in the winter when it's very cold, right? So then there comes this appearance aspect, and then comes the second aspect, which is the appearance in the particular setting. So then we can generate a lot of this kind of data, which can be used for training any kind of networks, whether it's attack detection or recognition application and so on. And then you have the second problem, right? Let's assume that we want to use all the data that we have, real data, for training so that our systems become better. What do we evaluate that on? So we need new data, right? Now to bridge this gap, what I could do is I could either train the data using synthetic or evaluate it on the real data, or I could do vice versa, right? So one of the example here is that I could create multiple faces per identity, and also I could create multiple faces of existing identity. So given one image, I can create multiple images of the same person, right? And then we have the third aspect, which is on attacks. So if I want to simulate how this person would look like if I'm going to print his picture and use it for his bank application, right? Your bank is typically taking a face image, and then you're just getting into that because it looks and says, okay, this is certain person X. Now, if I'm having the access to the picture, the photo of that person, I can present it back, right? So what I could do is in synthetic data, I could learn the characteristics of this printer, and then I can add that pattern of printer onto the face image, and then I can present it back, right? Make sense? No? Okay. Okay, let's assume another example. Let's say that I know how I would look if I wear a mask, and then I know how everybody would look when you're wearing a mask. And if I learn the pattern of how the mask would look on image, I can use that idea to create this lot of synthetic images with masks on. So I don't need to go and ask people to wear the mask and correct the picture, right? So which means it also allows us to do a lot of research without actually involving the subjects by synthesizing these kind of images. And then there is this other bigger aspect, right? The bigger aspect is that if you are interested in finding out, okay, what would happen to all the face recognition system if there is no beard in the picture? So what you would do, you would have to ask everybody to shave and then take the pictures, which is very unlikely. And then what we could do is we could say that, okay, I remove this attribute and then I create the synthetic data, right? Such kind of fine-grained control is available in the synthetic data. And now how do we achieve this? Now go back to the conditional GAN. In the conditional GAN, I could create a vector where I could say that what are the attributes A, B, C, D, E, and one of the attribute is muted. I mute that attribute and I can create the data, right? So that gives the flexibility for creation of data. And then is the last part, right, which is on privacy enhancement. One thing is that how do I make sure that my data is not being misused? Which we'll talk about this later in one of the sessions. But if I want to be completely eliminated from the data sets, how can this be achieved? So there also comes the idea of using the synthetic data. So I don't necessarily need to give my real data, but I can give my appearance data, which can be used to create this synthetic data, right? Once I have the synthetic data, I could use it for various purposes. Okay, and not just this one. And then there have been number of works that have been done in the last couple of years, which I'll give you some sample images of, sample explanations here. And then you can, of course, go into these works. Every reference is noted in the bottom part, so you can read these references. And most of the papers are also available on the archive. Okay, so in this case, let's assume that we have some authentic images which are on the top here. Person A, B, C, D. Oh, sorry, the same person, the images A, B, C, D. Are you able to see? Yeah, okay. Get laser. So here you have the same person. And then if you are now going to generate the synthetic images of that person for the same one, you start getting images like this, right? So if I just zoom it in a bit, you can see that this face and this face are not looking similar. This and this are not looking similar. Now this one maybe to some extent, this one maybe to some extent, right? So then there is a problem of labels. And the same thing can be seen here, right? So if I have a particular idea of this person has appearance which is changing all the way from having beard and mustache to no mustache, no beard, right? So this appearance changes will again lead to another problem. So what can you do in this case? Now you can kind of segregate. Okay, so now what you can do is you can take this authentic data. In this work, they took 10,000 different identities and then pushed all of them into the network by taking the embeddings of each of those network. And the embeddings now here are face recognition embeddings. And they take those network and they take it as latent space now, right? It is nothing but Z space, whatever we are talking about so far. And then you can introduce them with augmentation. With the augmentation, you go back to the problem of optimizing, and the problem of optimizing means that you can now suddenly get number of data here, which is the generator loss and the discriminator loss, which is the GAN architecture, right? So as soon as I have this one, so now I can go from that identity to this identity. And now the idea here is that based on some identity which is available in the training network, in the training data set, I can create new samples, right? So there is this, you can introduce new classes, which means this is very effective method for creating synthetic data, right? So here we are specifically looking at this aspect because if you are trying to generate the images of tree, nobody would really care about if it is a mango tree and the coconut tree, right? Unless you really want that one. In our case, we want to keep the identities of the face, which means Pranav should look like Pranav, right? And if it doesn't look like that, then the whole point of the generation process is defeated, right? So that is the idea here. So to do that, we need to constrain some ID, and the problem of labels was solved in this approach called as S-phase. Then they discovered one more thing. Any two faces which are close enough should be in the same angular space, right? If I have two vectors, I have two vectors, A and B. What is the angle between these two? Cos of is 0. Cos, so cos theta where theta is 0, right? These are completely orthogonal. The distance. Now what can I do? I can and tell that, you know what, every time you are generating, the image lies in this particular space, plus or minus theta. So when I can say that I want it in less than 10 degrees, but then the diversity of the samples. So you can give a bit of margin and say that, well, so now the GAN itself is, but instead of having this, the loss part here, now if it's cross entropy loss, there is BN loss, and then, so now this margin based losses are, gets constrained. Oh, every time I touch this, it goes away. Okay, did you get the idea of how we are concepts which are more realistic? You can understand the math later, just get the idea that two vectors, whatever we are trying to generate, should be, cannot be completely different. Yeah? They identified the problem in the next work and then they solved the problem as well. And in this case, they say that okay, the generator has to be consistent to recreate the identity all the time. also spoke about this problem of normal GANs and condition GANs, right? Class condition GANs. And the same problem happens here. You have this vanishing gradient problems, and then you have mode collapse problems. One. So now in the case of only class, which is nothing but identity, the variation in the data is strongly followed by the generated training data. The daylight conditions, your output images will also be only in the daylight conditions. Now, which defeats the whole purpose of having this generator, right? The synthetic data. So how do I do this? I can now condition the data by using the conditional GAN, and then suddenly I have different images. So how do they do that? Anything that you're looking at in the embedding space should lie in the same area. We have been talking about all the time. And now you extend the idea here. Now you are looking at this same from the same subject, irrespective of what condition they are taken in, they should be lying in this area. If it is not lying in this, and this person's face may be somewhere here, which is not lying in the space that we want to. Don't expect you to understand the whole math right away, but do you understand the notion that the embedding space should be in the same area to generate better images, right? So now if you relate, the data is different. The data is the face data. Okay. Okay, and then work that was published, and in this case, in the previous slide, I showed you that generating variations based on already existing based on the extracted face embeddings, right? And then we also showed that to create new synthetic samples, synthetic identities, the are very close. If they are not close, then they are not respecting it. And then we have this the third one where we are trying to look at the synthetic. So here you see that there is a denoising unit in the bottom part. So all this is doing is that it's taking the generated samples. And there is a pre-trained variational autoencoder, which is here, which is the denoising unit, and then you're trying to create the new samples. And now remember, the 0 and 1, mean equals 0 and standard deviation equals 1, which comes here, and then the discriminator generator model comes here, and then to tell you that all the things that you have learned together in the last 2-3 days, you can put them together to create better content. Do not go for the base content where okay, and then if you have this ID face, they also showed that which is called LFW, and then they try to simulate different variations such as people wearing sunglasses, people lighting condition changes, the pose changes, the angle changes, and so on. So in identities were very clearly separated, so they were not indicates that by carefully putting everything in new systems. And then there is one other application that I want to show. Two applications. this is a problem. The transition of Michael Jackson from 1970 to 2005, whole of his ethnicity changed, right? So from he became white skinned person, which is one thing, but if you look very closely into the images, you also see that the face image itself has changed. The structure of the face image, the morphology of the face image has changed. Now, they also used for people gaining weight, losing weight, and so on. But at the higher level, it's much bigger, right? It's so what we wanted to do was, in fact, okay, I should also tell you that this was the work done by Professor Nithanen. That's Praveen, who is now a professor in different university in SVNIT. So what said, I have this gun with me, so the gun can translate anything to anything, right? So if I give a flower image, it can translate it to a tree image and tree. So he took all the images from people from India, and then he transferred them to another ethnicity if they were African. We're synthetically introducing the ethnicity, and once different ethnicity representation for same identity in your FRS, which is basically here, right? So which means tomorrow if I'm a white Caucasian person, you can still identify me, okay, which is unlikely to happen, but if it happens, you can still do it here, right? Again, there's a small number of unsolved challenges here. If you are interested, you can pick up this direction. Some of the challenges that I can show you, I highlight you, are here, right? So if you look into the specific features here, it's not fully coming here, right? The whole of the feature that should have been appeared here, it's not appearing. It's not appearing. And the second thing is also the Indian person here is not really looking like Asian, right? Why do I say that? Because very often you see that the characteristics of certain features in the face are very different. For instance, maybe they have smaller lips as compared to the Indian population, which is not captured here. Now all you need to do is that if you can introduce this DC gun and then class condition them, maybe you can get better results. Okay, and then okay, to illustrate the problem a bit better, maybe you recognize the celebrity here, and this is how the cycle GAN gives the results, and this is how different GAN star GAN gives the result, and this is the F GAN, which is all variants of different GANs, and they all are used. And in which case you can see that okay, maybe in the case of black, the skin color is changed, but still the appearance is not very well changed, right? Uh, like this, maybe now you can see that, right? And in the case of Asian, yes, it has changed some of the appearance. The positions of the nose and eyes are changed, but not necessarily all the features. Okay? So this gives an indication that there is still a lot of scope in in this direction. Good. I know you had a very long day today. So how much more time? I have 4 more minutes to wind up. So I'll wind up with this last example. Uh, Here is the example of how GAN can be used to create deepfakes, right? So I did not talk about this, but now I'm going the reverse way. I showed you how to detect them, but in this case, I'm showing you how to create them. So the work that was done in 2019, again, not from our group, from a different group, they showed that it's possible to have this source to target video enactment by swapping the face, which is shown here in the central part. So here is a source image, here is a target video, and I want to transfer the expression of this person into this person, right? So this person to this person. So I can easily do it with FSGAN, which is which they claim to be subject agnostic, which means it doesn't matter who the person is. For instance, this person versus this person, right? And ethnicity, which is this person versus this person. And it's also very independent, agnostic to different minor changes like hairstyle, the appearance, and so on. And then in their work, they also showed that it's possible to not just simulate standard angles, standard poses, but also simulate the different poses. Which means here, if you have the real image, you have 0 degree, 20 degree, 40 degree, 60 degree poses, right? The person is tilting slowly. And for each of them, you can still transfer the expression. So for instance, with n equals 1, you see that there is a change. The expression has changed. Maybe I should zoom it a bit. Now, you see that the expression has changed, changed, and the same thing happens with, and the quality of the image becomes better and better as you progress in the terms of iterations. So this is to give you an idea on how the things can be used. But now, as you look very close into the image, can you look into the patterns that is coming here? Now you realize the fingerprints that I was talking about. So any kind of GAN images that you're going to generate, they're going to end up with such subtle patterns. And now you can use the subtle patterns to determine or to devise a new classifier. Okay, so remember, it's always a loop, right? So you design some approach and then you find out what is happening there, and then you can use that artifacts, the clues, to create the classifier again. And then this goes back to your GAN approach where you are looking at discriminator generator, make the discriminator better, and the generator becomes better, and make that better, discriminator become better. So it's like constant loop. Okay, I'm very happy to say that I can leave you 1 minute earlier than scheduled time. So, or we could use the 1 minute for any questions that you have now. No questions? Long day? Tired? I know it was a lot of information that we compressed today, but remember, all the slides will be made available. So if you have any questions, you could also look into that particular slides, and then you could also reach out to me if you have any open questions. Yeah. Oh, this one, yeah. What happened? That disappeared. Yeah, trying to put it back. Oh, I think that timed the projector also for 5 o'clock, so it doesn't work after 5 o'clock. Here, here.